Okay, so if we're looking at this last one, we have this velocity versus time graph. And when we look at this one, it kind of looks like what we're used to thinking about as a square root graph. We're kind of used to saying, oh, well, this kind of looks like a square root relationship. So what we're going to think about when we're comparing it to our sheet compared to what we're used to, and say, oh, this is kind of a graph of y squared versus x. Or if we kind of square rooted them, we would say y equals square root of x. So y versus square root of x. But really it's the same relationship where one is growing squared while the other one is kind of growing a little bit slower. So we really have at the end of the day, or at the beginning of the day, we're not at the end of the day yet. So what we really have is this velocity is equal to some sort of scale factor, some sort of slope, times t, and sorry, it's velocity squared. So we're saying, or really we could do it, yeah, we'll just do it this way. So say v squared is equal to a times t. So a is some sort of constant that's relating them. And again, really the reason we want to do this is because we don't know this relationship. We don't know this growth factor. And we want to be able to look at it and immediately be like, oh, well, this is how they're growing. So we can say v is equal to a times t. But what we want to do is, again, make that substitution so we can figure out how are these things related linearly? How can we create this linear relationship? So this is kind of my v squared is equal to at. We know that this will become linear if instead of v squared, we were just to graph v as a times t. We'll be able to get a linear graph if we just graph something that we're used to, this y equals mx form, this b, whatever. So we'd say, hey, if we graph it like this, we will be able to figure out a nice linear relationship between them. So what we have to do is make this substitution and say this capital V is equal to v squared. So then we can graph v equals a times t. So let's go over to our Google Sheet and let's do that. Oops, I closed out a bit. That's okay. So while that loads back up. So we said that we want to graph velocity squared versus time. So let's try that out. So instead of a velocity, we will be graphing a velocity squared. And again, we'll just take these values and we'll say let's square them. We've squared all those values. We'll copy our time values. And let's try it out. Let's make this chart. Insert chart. And there we go. We have a nice linear relationship between them. So then we can again go to customize, series, trend line, label, use equation, and we have this nice relationship. We can say the slope is 56.6. We can say the y-intercept is relatively small compared to the values on our y-axis, this velocity squared. So we can just say, that's close enough to 0. Let's say 56.6 times t. So we can say, okay, in this case, our a value, 56.6. So we can say that this v is equal to 56.6 times t. And then we'll sub back in and say v squared equals 56.6 t. Now I think I'll just cut the video here, or maybe let me. Sorry, so final comment about that is something that we could do too if we wanted to make it look more like a graph that we're used to, is then we could say we could square root everything and say v is equal to the square root of 56.6 square root of t. So then that'll look more like, hey, we have this v over here, and then we have the square root of our variable on the x-axis. That's how we usually think about it, instead of saying, when we're looking at the axis, usually we're like, oh, this is square root, instead of thinking about, oh, this is squared. So that'll just kind of put us in a form that we're more used to. So that's kind of a final wrap-up thought about that.